Estimation of very large and very small numbers. Part 1. Order of magnitude for very large and very small numbers. So you need to understand about orders of magnitude, an order of magnitude estimate of a number, how it's rounded, and what happens if numbers differ by an order of magnitude of 1. Then that number is approximately 10 times the other. Likewise, if they differ by a magnitude of 2, then it's approximately 100 times the other, and so on. An Olympic-sized swimming pool has a length of 50 metres, a width of 30 metres, and an average depth of 3 metres. It is proposed to fill this pool from empty with a garden hose which can deliver water at the rate of 1 gallon every 6 seconds. Using order of magnitude estimates, obtain a rough estimate of how long it would take the hose to fill the pool. Is it hours, days, weeks, months, or years? And you need to note that 1 gallon is 4.546 litres. What we are really trying to determine here is if it is reasonable or practical to try to fill an Olympic-sized pool with a garden hose. So order of magnitude estimates for the dimensions of the pool are as follows. The length is 50, which is equal to 5 times 10 to the power 1, which is approximately equal to 10 squared. The reason for that is the 5 will round up to 10, which is really 10 to the power of 1, and 10 to the power 1 times 10 to the power 1 is 10 to the power 2. The width of the pool is 30. 30 can be broken down as 3 times 10 to the power 1, and that's approximately equal to just 10 to the power 1, because the 3 will round down to 0. So we're just left with 10 to the power 1. And the depth is 3, which is the same thing as 3 times 10 to the power 0, because remember 10 to the power 0 is 1, anything to the power 0 is 1, so that's really 3 times 1, which is 3. And this rounds off to 10 to the power 0, because the 3 will round down to 0, so all you're left with is this 10 to the power 0. Thus, if V is our estimate for the volume of the pool, remember the volume of a cuboid is the length times the width times the height, or in this case the length times the width times the depth, we end up with the volume being 10 squared, which we got from here, multiplied by 10 to the power 1, which we got from here, multiplied by 10 to the power 0, which we got from here. 2 plus 1 plus 0 is 3, so we get 10 to the power 3 metres cubed. Now remember, 1 metre cubed is equal to 1,000 litres. So since 1 metre cubed is equal to 10 to the power 3 litres, which is 1,000 litres, we also have the volume to be 10 cubed times 10 cubed, which is 10 to the power 6 litres. Order of magnitude estimate for the rate of flow. So the rate is 4.546 litres in 6 seconds. So we were told in the question it was a rate of 1 gallon every 6 seconds, and since 1 gallon is equal to 4.546 litres, that translates to 4.546 litres in 6 seconds. Dividing that by 6, we get 0.7576, which rounds off to 0.8. So we can rewrite this as 0.8 litres in 1 second. And that is approximately equal to 1, because 0.8 rounds up to 1. And 1 is the same thing as 1 times 10 to the power 0, since 10 to the power 0 is really 1. That's really 1 times 1, which is 1. And this rounds off to 10 to the power 0. And it's 10 to the power 0 litres per second. So from our formula for rate of flow, which is volume divided by time, we swap the rate and the time. We basically solve for time. We get time is equal to volume divided by rate. The volume is 10 to the power 6. This is on the previous slide. And the rate is 10 to the power 0, which we got from up here. 10 to the power 6 divided by 10 to the power 0 is still just 10 to the power 6 seconds. So how long is this? Well, we know 1 minute is equal to 60 seconds, which is approximately equal to 10 squared, because 60 would round up to 100. So it's approximately equal to 10 to the power 2. An hour is equal to 60 minutes, which is approximately equal to 10 squared, because 60 would round up to 100. 10 squared is 100. And a day is equal to 24 hours, which is approximately equal to 10 to the power 1 hours, because the 24 would round down to 10. It would not round up to 100. It's closer to 10. So 10 to the power 6 seconds, which we got from here, our time, is really going to be 10 to the power 6 divided by 10 squared, which we got from here, multiplied by 10 squared, which we got from here, multiplied by 10 to the power 1, which we got from here. And 10 squared times 10 squared times 10 to the power 1. 2 plus 2 plus 1 is 5. That's really 10 to the power 5. And 10 to the power 6 divided by 10 to the power 5 is 10 to the power 1, which is 10 days. So our order of magnitude estimate is in weeks, which is clearly too long from a practical point of view. So we would estimate that it would take weeks to fill the pool using a hose. Part 2, estimation of large numbers. Una wants to estimate the number of books in her local library. She makes a few quick calculations. There's 68 bookcases of a width of 80 centimetres, each containing 6 shelves. Each shelf contains on average 35 books. There's 21 bookcases with a width of 50 centimetres, each containing 5 shelves. Each shelf contains on average 16 books. There are 10 bookcases with a width of 40 centimetres, each containing 4 shelves. Each shelf contains on average 10 books. What estimate of the number of books will she obtain? The bookcases of a width of 80 centimetres contain 68 times 6, which is 408 shelves. So 68 times 6 is 408 shelves. Each contain an average of 35 books. This gives approximately 400 times 35, which is 14,000 books. So the 408 was rounded off to 400. The bookcase of a width of 50 centimetres contains 21 times 5, which is 105 shelves. So 21 times 5 is 105. Each containing an average of 16 books. This gives approximately 100 times 16, which is 1600. So the 105 was rounded off to 100. The bookcase of a width of 40 centimetres contains 10 times 4, which is 40 shelves. So 10 bookcases, 4 shelves, gives us 40 shelves, each containing an average of 10 books. This gives approximately 40 times 10, which is 400 books. Una's estimate for the total number of books in the library is 14,000 plus 1,600 plus 400, which is 16,000.